Hi. Like Ani said, I've been here like a few times and I guess collaborating with Luke and Ali a lot. So there's a good chance you've heard a lot of the stuff in this particular slide deck. But I try to put in some kind of like new spin, and there's actually some new stuff, like Ani said, at the end that hopefully is a little bit exciting. And so in general, my research kind of like spans two broad areas. One I kind of call grounded intelligence, which is kind of the stuff that Annie talked about, like situation recognition, like making objects like avatars from descriptions, or like some common sense, extracting common sense. But I also have this other part of my research, which is like about communication and language generation. So I've done some work on simplification, describing images, and we have some new work about kind of generating from something called AMR, which is a formal kind of meaning representation. And in this talk, I'm actually going to focus more on the grounded intelligence stuff. And I'm going to kind of try to unify a subset of the work under a theme that I'm calling language as a scaffold for accelerating grounded intelligence. And OK, so what is grounded intelligence? Well, it's like you want to put kind of an agent into the world, right? You hope they learn something about perception, about reasoning, and about action. And you want them to kind of like behave well and not mess up in the world. And potentially do useful things for people, but not necessarily. So here's one potential story of a developing agent. It's like you put them in a garden. They kind of wander around for a long time. They explore. Maybe eventually one of them stumbles upon something, and they look at it, and they name it. And they call it a flower. Okay? And another kind of agent realizes this and is excited. You know, there's a flower. And all the agents now know there's a flower. And the vast majority of agents now kind of don't do much that's too interesting with a flower. Like mostly they just stare at it. Like some poor guy tries to like run it over, which isn't really a fruitful activity. Some people might pick it and decide, oh, maybe we can like extend our arms forward and try to do something with it. But that's also not particularly a useful thing to do because kind of like presenting a flower into space, you know, nothing happens. And eventually, maybe somebody discovers, well, you can do this awesome thing with flowers. You can take a flower and you can give it to another intelligent agent, and this kind of has some kind of good consequences. Maybe there's some social building. And so after that happens, every agent can know that there's a flower and that there's giving a flower, and they can kind of explore and go forward again. And kind of the big problem is, do these agents have to start over every time to kind of like go and rediscover a flower and rediscover that we can give a flower? Or is there a way to actually make that process faster? Okay? And so kind of the proposal is, well, maybe we can combine some sort of language to inform an agent about what's in the world and how it functions, and then make this kind of like exploration process like more scalable. And so I'm going to talk about three works in that kind of general area. I'm going to talk about visual common sense, which is kind of like spatial facts and how you actually use a resource like WordNet to quickly build up large amounts of spatial information, spatial common sense. Then I'm going to talk about situation recognition, which is going to be the majority of the talk. And then I'm going to talk a little bit about this kind of new thing, which is, well, if you kind of decide that language is going to inform how you perceive the world, what does that do? What kind of implicit things are we actually going to teach agents about what we believe about the world, and how much is it coming from like our biases about the world, maybe not good ones, and how much of it is actually just teaching agents about the world? So I'm going to talk about common sense first, and this is a project that I did actually here at AI2 over a summer. This was a hackathon project that turned into a paper. And basically, this was with Vicente and Ali. It's called Stating the Obvious and Extracting Visual Common Sense. And so one kind of question is like, OK, what is visual common sense? OK, so visual common sense is not being surprised if you see this cat on a bed, not being surprised if you see a horse in that stable, not being too surprised if you see this cat in the stable, but if you see a horse in a bed, you might be like really, really surprised. And so that's common sense. And kind of the big problem about it, if you kind of like look through NLP, is like, well, OK, it's rarely stated explicitly in text. And it's really hard to get people to produce it exhaustively. And so kind of the idea behind this project was, well, OK, we have some densely annotated images. There's this corpus called COCO, and basically covers 80 objects. It's 125,000 images, only covering how these objects co-occur. And how's the data set up? It's basically set up with regions. Each of the region comes with the label from each of these 80 categories. So the basic idea is, well, why don't we look in here to actually extract large amounts of common sense? And the big problem is, well, there's like only 80 objects. What could you possibly learn about the world from like 80 objects? And so I'm going to show you a way in which basically I'm going to first use COCO to observe the world and observe lots of very high quality information, but not too much of it, and then actually scaffold on WordNet to generalize to hundreds of thousands of common sense statements about the world. So here's the basic setup. We're going to take an image in COCO. It comes with regions, and we're going to define a calculus of the way these regions can interact. And so this calculus is basically, there's different versions of it. Basically, it's the set intersection of ways of the way two regions can interact and a kind of a subset of them. So we use things like touches, besides, on, inside, hold. And there's kind of like different versions that you can do of this, but it's not really too important. And the basic idea is, OK, you're going to compute when two regions interact, and then you're going to compute just some summary statistic on when these two regions are interacting, what is the kind of identity of the object that's involved in the interaction. OK? So we're going to do something like compute mutual information between like an interaction, an object, and an object. And then we're just going to rank by mutual information. And so what kind of common sense can you get by doing this? You can get, so here I'm showing a table of things we extract. On the top is things which are likely common sense. On the bottom are things which are kind of supposed to be unlikely. So people can hold ties is a high-quality common sense statement. People do not tend to be above buses is another statement that we derive. You can kind of like use this setup to query interactions within a particular like type of objects. So frisbees on the left. So dogs tend to touch frisbees, which kind of makes sense. People aren't actually found above frisbees because that would just be a really strange world. So doing this, we can actually extract around 6,000 high-quality statements of common sense. But kind of like, that's not that much, right? How do we actually go further? And so the basic idea is, OK, we're going to use WordNet to actually extend our knowledge. And so here's the setup. We want to find a set O such that all things in that O can be, for example, on a table. OK? And so what we're going to do is we're going to start with the categories in MS COCO. There's 80 of them. For some of them, we observed that they can be on tables. OK, so knives can be on tables. Bowls can be on tables. OK? For the ones that we didn't observe that could be on tables, we're going to assume that they can't be on tables. OK? So these are things like refrigerators and cars. And basically, we're going to take these categories and put them in the larger context, larger linguistic context of WordNet. OK, and we're going to say, OK, so some of these items have hypernyms. Right? So for example, we had knife, which could be on table. Cutlery is a possible hypernym. Tableware, et cetera. There are some very, very broad categories like entity, which will cover lots of categories in MS COCO. And basically what we're going to do is we're going to try to push information up from the entities which were part of the original common sense to their hypernyms, and not push too much such that we would imply facts that weren't true in the underlying MS COCO dataset. And then once we have these kind of high-level statements of common sense, we'll try to push them down to the kind of descendants, the hyponyms of these hypernyms, and then we're going to get lots and lots of kind of implied statements of common sense. So this will give us a large set of things, for example, which could be on a table, which weren't originally in MS COCO. Yeah.
Is now a good time to ask a question?
Sure, go ahead.
So it seems to me, right, that the basic setup makes a lot of sense, and this is about implicitly generalizing from a limited amount of data. But let me put two things side by side. One is what you did, and the other one is identifying properties of the objects would drive that. So for example, let's suppose you didn't happen to see any insects on the table.
Mm-hmm.
Then this thing will not generalize, it will say no insects on the table,
Yeah.
because it's making a kind of closed
Yeah.
world assumption.
Yeah.
On the other hand, if you generalized about size and weight, and said basically anything could be on the table so long as it's,
Sure.
so I'm just wondering, does that make sense?
Yeah, absolutely. Yeah, I don't think this is the only way to generalize the common sense. I think this is like a category kind of way. And the nice thing about this is it kind of like uses kind of existing knowledge already to do it. That's kind of encoded in WordNet. The size stuff, you'd have to kind of like infer it somehow, so.
Using all these other questions. No.
Maybe.
It's a potential next step.
Yeah. Yeah. Okay. Yeah, so basically kind of on the technical side, you can formulate this problem as a submodular K-cover. And I'm not really going to go into any of the details, but basically we can use this to extract over 400,000 actually new statements of common sense about objects not in MS COCO. And what kinds of things do we discover? These are kind of the high-level rules. So, a dining table can hold cutlery, edible fruit can be found in a bowl, domestic animals can be found on a bed, things like that. So in terms of a little bit of quantitative analysis, obviously common sense is very, very hard to evaluate, but the way that we actually do it is we give it to mechanical Turkers and say, how surprised would you be if X happened? And then we get lots of judgments because it's super, super noisy and just kind of average. And so this is a graph showing the quality of our original kind of common sense that we derive on MS COCO. So the black line is all of it. The red line, or the green line is kind of on people, and this is random. So we do much better than kind of like generating random statements from the world as facts. We do much better on people because the vast majority of, and I don't know if you've looked at MS COCO images, they're like predominantly of people. So we learn better common sense about that. We also, yeah, so this is 6,000 facts. So this axis runs from 0 to 6,000 for all, or 0 to whatever the subset was of the particular slice. So like person.
And
Yeah.
the ordering is based on internal confidence?
Yeah, by the mutual information, yeah. Yeah.
It could also, so you said that you do better on person because most of the images are about people. It could also be the case that more facts are true about people in the space of things that you're considering. Like, is that possible? Did you consider that?
That's probably true. Yeah, that could definitely be it too. I mean, yeah. I mean, we're like the most productive object in those images, yeah. Yeah.
Do you try any other baselines, like just using co-occurrence in text? Basically saying X is on Y if they have a co-occurrent text. And how different is that from random?
We didn't. We kind of tried just focus on the grounding setting. Yeah, I think this work could have definitely used some more kind of baselines, but I think it was like the first kind of work to like really like peel at how you use COCO or like some like high quality image annotation to actually derive the common sense.
So most of the relations are not reflexive, right? So if you're just using co-occurrence, you'd at least need the directionality of the
Yeah.
relation somehow.
Yeah, I mean, there's a lot of ways of getting around that, but
Yeah.
may or may not work well.
Yeah, the other thing is like in general, I mean this isn't, I mean I didn't explore that for this particular work, but in general I found like the coverage of grounded kind of like concepts in text is kind of low. So at least like in some work we've been like looking at like finding what is the text to derive common sense for the grounded world, and it's like just really hard and we don't know, and we just like keep looking at stuff that doesn't work. So yeah. Yeah.
I might have missed this. How do you control how much generalization you use in programs?
Yeah, so this kind of fits into the submodular K-cover. There's just some details, yeah, that I'm skipping over.
Some heuristic about,
Yeah.
I mean, everything's a thing. You realize that too as well.
Yeah, so I mean, so the way the submodular K-cover basically works is it says, well, you're gonna take a penalty when you imply something that's false in COCO, and you're gonna get points if you expand the set of facts that you know about. So And then you just, like, there's a parameter to trade those things off. Yeah. Okay. Yeah, so basically we evaluated the generalizations too. They're also pretty reasonable quality. Okay, so now I'm going to go on to situation recognition, which is kind of the bulk of this talk. And just to summarize, basically I showed you how you could take 6,000 kind of common sense statements that you derive from directly observing a grounded context like Coco and use language resource like WordNet to generalize it to kind of like hundreds of thousands of new statements of common sense. And so now I'm going to talk about situation recognition, which is kind of formalism we proposed for modeling events in images. And again, it kind of uses these linguistic resources to bootstrap. So this is a project I've been working on for a couple of years. It's in collaboration again with Vicente, Luke, and Ali. And here's the basic motivation. So it's how do we summarize what's happening in an image? And for us, the proposal is basically, well, we're going to try to introduce this structured representation, and it's going to involve a verb. So for example, loading. It's going to involve lots of relevant objects, for example, woman, horse, trailer. But kind of like crucially, it's going to also say how those objects are interacting within the event. So it's not just that there's a woman or a horse, but also the woman is the one who's loading the horse. The thing that's being loaded, the item, is the actual horse. Where's the horse ending up? That's the destination. It's in the trailer, and so forth for these other kind of semantic roles. And so kind of like to understand why this is important, I think maybe you guys have seen this slide before, but basically we ran this kind of lightweight Turk experiment where we gave them two sets of images and asked them, is the same thing happening in an image? So given these two images, kind of on a high level, you know, in both images, pouring is happening. In both images, beer is the thing being poured. Glasses are involved. People are doing the pouring, right? But if you ask Turkers, like, is the same thing happening? In general, they say, you know, in some sense, but predominantly no. And if you ask them why, they're actually very, very good at saying, you know, what the difference is. And really, it's about not just the objects, but how the objects are involved in the event. So in one case, the beer is ending up in the glass. In another case, the beer is actually coming out of the glass, right? So in one case, it's a destination. In the other case, it's a source. And so basically, we've introduced a problem we call situation recognition around this formalism. The basic setup is you're going to take an image, and you're going to produce this kind of structured representation. And this structured representation is potentially going to be different for every verb. So for example, for fixing, we're going to have something like object, the thing being fixed. There's going to be a tool, the tire iron, etc. And so one kind of central question in this work is, what is the space of possible situations? How do we know, you know, what these kind of structures are? Where do we get them? How do we fill them? And also, how do we build effective models? Last year at CVPR, we introduced this data set. This is like predominant. It was basically completely collected here at AI2 a few summers ago. And it's a large-scale kind of data set for this formalism. And kind of the way to think about this is that it's actually the reverse situation as what I presented for common sense. We're actually going to use resources to define a problem so that we can actually learn better in the world, as opposed to using resources after learning in the world. So what's the setup? Basically, to kind of understand what the space of possible situations are, we kind of reach to natural language processing. You guys probably are familiar with semantic role labeling. If you're not, the basic setup is you're going to be given a sentence. So for example, a boy's fixing a car tire with a tire iron outdoors. In it, you need to identify a verb. So for example, fixing. And then you need to label spans in the text as arguments to the verb. So for example, boy, fixing a car tire, tire iron outdoors. And for each of this span, you need to classify the span into a particular set of semantic roles. And the way you get these semantic roles is they're actually usually coming from an ontology. And in it, usually every verb kind of has its own set of semantic roles. And so what we're going to do is we're actually going to build a situation recognition around these resources. So we're going to use FrameNet, which covers 8,000 verbs for an ontology of verbs and semantic roles associated with those verbs. And because we don't have sentences, we need to fill the values with entities that are in the image. And so what we're going to do is we're going to use WordNet to fill values. And so how do we actually build a data set? And so once we've defined the actual structure of the problem, we need to find images to actually annotate with what's happening inside them. And so what we do is we actually just use Google Ngrams and Google Image Search to retrieve some number of images, have Turkers decide, is an activity happening in that image or not? So in this case, they'd be presented with that image. It would have been queried with some sort of fixing kind of Ngram, and you say, is it fixing, is it not? Some say yes, some say no. And then once we have a set of images that we know an activity is happening, we take a frame, which we get from FrameNet, and actually let Turkers fill in the values. So around this, we've actually collected a pretty large-scale data set. It covers 500 verbs, 125,000 images, covers over nearly 2,000 kind of semantic roles. And this is actually kind of the largest scale data set in terms of verb coverage and in terms of noun coverage. And it turns out that the agreement for actually filling these values on the bottom, despite having to pick one of 80,000 possible noun synsets from WordNet, 2 out of 3 annotators agree over 75% of the time. So data is pretty high quality. OK, so I've shown you how we actually gather this data, how we actually define the space of possible situations. It's around these resources. And so how do we actually build effective models? And so the basic setup is we're going to combine structured prediction and deep learning. And the idea is we're going to take an image. You're going to use whatever your favorite current convolutional neural network is. It's going to predict some sort of features. And you're going to use these features to regress to potential values in a conditional random field. And the conditional random field is going to look like this. It's going to be somewhat star-shaped. Basically, what it's going to do is it's going to condition, or it's not going to condition, but it's going to put a potential between a verb and a value of a semantic role. And all the semantic roles will be independent given the verb. Yeah. Sorry, what?
In the data set, you said there's an average of like 3 situations per image?
Yeah.
How does that get handled here?
Yeah, so the way that that's annotated is basically it's the same verb and it's different noun values to kind of like give variation to possible different ways to refer to the agent, for example. So this could be man, but it could also be worker, right? And so the way we handle it is just kind of a noisy or objective on top of this. So we don't just optimize the CRF likelihood. We optimize the likelihood that at least one of the annotations is satisfied. Yeah. And given that particular objective, we actually optimize it all the way back to the visual recognition layers. OK, so just using this kind of like pretty simple model, you can get some pretty interesting results. So basically, if all you care about is predicting activities, is it better to predict this entire structure and then marginalize for activity, or just train a deep neural network just to predict the activity label? So it turns out for these images, it's actually better to pivot through the structure than to train an independent classifier. You can ask the opposite question. If all you care about is objects involved in an activity, is it better to train a deep network just to predict these object categories, or is it better to pivot through the structure and actually kind of like do the right inference to predict which objects are in the image? And it turns out it's actually much better to pivot through the structure. And the kind of like rationale for this is imagine you're talking on a phone, right? This phone in context is quite small. If you're kind of taking the picture this way, all you see is this kind of edge. And it makes sense to use the entire context, for example, that it looks like I'm talking on the phone to actually predict the existence of the phone rather than just independently doing it. Yeah.
I'm a little bit confused. So first of all, I'm assuming that the contrast between the whole system versus just the neural net baseline is the contrast between the background and the related line. Do I have this right?
OK. So objects here, so situation is the full structure, doing situation recognition. Object is just doing object recognition or object classification. Is it in the image or not? An activity is just doing activity classification. Is the activity happening or not?
Okay, but you're contrasting a baseline of just a neural
Yeah.
network with the entire system.
Yeah.
So where is that contrast? What two lines do I look at?
Okay,
It's the
so
adjacent ones, I assume.
yeah.
That's what I was trying
Yeah.
to ask.
So the brown one, yeah.
Right, so when I look at that, I see two things.
Uh-huh.
And, not to be overly argumentative, but A doesn't make a whole lot of difference most of the time, and it makes pretty substantial difference in one of the cases. That's not quite what you said.
Yeah.
I wonder if I'm mischaracterizing it, is one question, and then the other question is why does it make so much more of a difference in that particular case?
Yeah. So I think in general, like deep networks are quite powerful, right? And so what the internals are going to do, they still observe the same image, right? So they can still try to make the same distinctions as you're getting from like this structure, right? The thing that you're getting is you're getting a new objective that's actually structuring like how the neural network should learn, right? So you don't necessarily expect like huge gains. So this is like 1.5, 2 points, and that's actually kind of a lot. This is like kind of 10% here.
Is this F1 on the
This is just straight accuracy, right? Yeah,
Okay.
yeah. And the kind of intuition why it helps more for objects rather than activities is that like basically getting the activity is like kind of a broad context, and like lots of different things are going to kind of come in, and so the extra supervision that you're giving the like neural network by telling it, oh, there's also these objects is kind of small, whereas for the objects, when you're saying they're actually involved in the activity, that's actually a lot of information because there's actually very little visual evidence for the object independent of the activity.
So one way to quantify this would be in terms of the amount of training data, right? So these gains, if you were to give it 10% more training data, or if you don't have 10% more, you could do 10% less, and see, did you try to quantify the win in terms of number of training examples?
Yeah, so I guess you're suggesting that we should see more gains at less data if we introduce more bias based on the structure.
Yeah, or even just, how many more examples do you need to see in order for the neural network to catch up to, the combination with the structure thing? That would be one way to think about how much you're gaining.
Yeah.
And if it's 5 more examples, that's not that exciting. If it's 50,000 more examples, that's more exciting. If you can't catch up, right, if the deep thing asymptotes, that's particularly exciting.
Yeah.
Have you done any of those?
We haven't. And I mean, I think in the limit of huge data, it probably would like kind of just go together. But I mean, the thing is, we're not just doing any one of these tasks. Okay, so actually, the structured prediction itself is a new task that the neural network can't do, right? So it's actually saying how these objects are involved in the activity, which is like a true statement about the world that if you don't use the structured predictor, it's kind of hard to get, right? So it's in evaluating the neural networks on the neural networks game, you can get these kinds of things. But there's a new game, which is kind of situation recognition.
And there isn't another simple way. That's a great point that you're making. And there is another simple way to recover the structured statements from the neural networks?
Well, if you supervise the structured statement, I mean, not without supervising them.
Okay.
Do you have a baseline where you treat the whole big structure as one discrete thing? What would happen then?
Yes, I do. Can you? Yeah, so like Luke said, there's another baseline, which is basically saying, does it make sense to try to decompose in this particular way, or can you just like wholesale predict the entire kind of thing as its own class? It's actually like very, very hard to predict the thing wholesale. And I guess I'll show in a little bit later kind of why this is. So, yeah.
So does this actually say that you're improving the state-of-the-art in object recognition by 10%, or is this just on a particular data set?
On a particular data set. So this is in the context of images where something is happening.
On standard ones, nothing's happening, it's just the image.
Like predominantly in, say, Cocoa, like very, very little is happening. And if something's happening, it's one of a few iconic things. Yeah.
It's usually very clear what the image is in those data sets as opposed to like a thought being used.
Sorry, what?
It's
I mean, they have phone being used, but it's like part of the thing is like if there's a small number of things happening, then this kind of setup doesn't make as much sense. But if there's like a huge set of possible things, yeah, then you expect this. I think you expect to see these kinds of gains. At least for activity recognition, these are kind of like some unpublished results. But like for like Stanford 40, which is kind of like an activity recognition data set in still images, kind of if you annotate this kind of structure for them and use the structure for your recognition, you actually have a state-of-the-art result. But yeah. Yeah.
Have you tried just to run this on ImageNet object recognition to see what is the accuracy do you get?
We haven't. The thing, the way this data is sampled is very, very different. So it's uniform over verbs instead of uniform over objects. So I wouldn't necessarily expect it to do super well. Yeah. Okay. Are you guys up for a demo? After Annie's endorsement. Okay. So these are possible verbs in the system. So I have some of my favorite. You could pick a random one or whatever. Basically, we have this website. It's imstitute.org. In it, you can kind of browse around, see the structure of these things. You can just completely just interact with the data. So if you wanted to know what can horses do, there's just a query for that. So for example, horses can rear. Horses can be the thing which is ridden, so they're the vehicle. Horses nuzzle. Horses can be involved in a jumping, so they can be the source, involved in a falling, so they can be the source of where somebody falls from. So this is kind of the way the data looks. Okay, somebody propose a verb. Dancing. Okay, let's go with a couple of dance. Okay, pick an image.
Second row middle.
Second row middle, this one. Yeah, this one? Okay. Okay, you can just put in a URL. And so what is this? This is the top K predictions ordered by verbs. So the top row says it's a couple dancing on a stage with confidence 25%, which is the top prediction. Let's try another one. Cutting? We don't have cutting. Let's try clipping. So the way the data is collected, basically, for some common verbs, they tend to have multiple senses. So that's kind of something we punted on the initial collection. So like common verb like playing, that can have the sense of like playing or playing. So, or like cutting. Was that licking? Okay.
What's your browser saying?
Let's do a different verb. Biting? No? Okay, fine, licking. Okay, licking ice cream. Okay, yeah. Okay, which of these should we go for?
First image.
First image, okay. Okay, so we got our first prediction is it's a male child tasting an ice cream with their hand. Second prediction, it's a male ice cream licking a child. Or, sorry, right. Or that it's a male child eating some sort of food, which we don't know. Yeah.
Do you want more action verbs or like more passive verbs like looking where action is being,
Yeah.
so like does it generalize to that or is it only limited to action verbs?
So again, we kind of only focus on more active verbs. Part of the thing with like a verb like looking is it's something I call a dense verb, which is that in a particular image, it's like just super likely to be happening. So like no matter what image you take of people or anything with eyes, they're always looking. Which kind of like makes the learning setup a little bit hard. Yeah.
Why is the place different in every, or not in everything, but why is it so different between frames?
This is good reason to move on, but basically, the reason is basically that there's not sharing between the roles. And kind of the next work that I'm going to talk about, which was just accepted at CVPR, is about kind of like putting more sharing into the model to kind of do better and kind of eliminate some of that stuff. Yeah, so this is more in the frame of how do we actually build models that work. And so this is a work, I guess I didn't put the collaborators, but Vicente was on this, Luke was on this, and Ali was on it. Basically a work called Commonly Uncommon. And so kind of the thing to think about is, okay, well, you've built this system, how do you actually want it to generalize? What is kind of like the goal? And so the kind of most common thing that happens right now in computer vision is you take an image, right? In some sense, the same classification needs to come out. So if it were a dog, there'd be like 100 images of dog, and you'd always want to say dog. And the difference between the image would be things like perspective, lighting conditions, maybe variation in the object. It's like a brown dog versus like a black dog, right? And so I call this kind of like generalizing to unseen views, but the underlying thing is that the semantics that you want to generate is always the same. So in this case, it'd be, for example, jumping. This is jumping images. A person is jumping from a cliff into water outside, right? And we have 15 instances of this kind of semantics in our training set, and we expect the model to do very, very well at it. Another kind of generalization you might want is kind of generalizing to unseen combinations. And so what does this mean? This is that the semantics you want to predict in kind of whole are unseen. So here's an example of that. So in the training set, we've seen 35 instances of feeding from milk from a bottle. We've seen 7 instances of a horse being the thing which is eating, but we've seen no instances when the horse is being fed from a milk bottle milk. And so how do you actually build models which generalize to that? And so, of course, there's kind of like a spectrum of this, right? It doesn't always have to be like this extreme case that you're predicting something that like you've literally never seen, right? You can basically say, well, how rare is a particular piece of the semantics that you need to predict? So like as this number tends to 1, right? You've only seen one instance of a particular piece of semantics you have to predict. How does the system behave? Okay, so this is exactly that graph. So along the bottom, I'm saying, what is the number of samples in the training set of the least observed piece in the semantics you have to predict on a development image, so on an unseen image? And this is the verb accuracy. So not even the accuracy of predicting the individual pieces of the structure. Can you get the overall activity right? And so basically, on the far left of this graph, you see things which are like very, very common. Like the least seen semantics has been seen in 100 training images. And so you actually perform very, very well. This is like the level you would expect to see like object classification results on ImageNet. It's like high 80s or something. Okay? But as you get down this curve, the performance just kind of plummets. So once you've seen things 10 times, only 10 times, a particular piece 10 times, the performance just kind of steadily decreases. Right? And this is actually even one particular rare piece. So if there's any one part of the semantics which is rare, you're basically done. Yeah, exactly. And so it turns out in this particular set is 25% of images in the data set. So this makes up a lot of the data that you actually have to, in practice, deal with. So basically, we've looked at 2 ways of actually dealing with this problem. One is building better models. So this is kind of like encoding more sharing. Another is kind of leveraging the connection of situation recognition to language to actually bring in more data and get even further up this graph. So I'm going to talk about the kind of like modeling stuff first. So we're going to basically look at the same model, but look at one particular part of it. So we said as a particular like verb, role, noun gets rare, our performance goes down. So we're going to look at reparameterizing how that particular piece of the model works. So how did it work originally? Because I didn't really go into any detail about it. Okay? So the setup was basically, we're going to take an image, right? And then we're going to get some sort of visual representation for that image. And what we're going to do is, in that baseline system, we're going to have a set of parameters which is unique for every verb, role, noun combination. And it'll be a vector, which says, I'm expecting these types of features from the visual recognitions, from the general image representation. It's just going to test, are my features matching with what's in the image? And for every unique verb, role, noun, I'm going to have a unique vector. So there'll be, in the baseline, there's absolutely no sharing between, for example, nouns or roles or anything. And this is how that's a potential setup. And so kind of the new idea that we have is to introduce something we call a compositional conditional random field. And the setup is, I guess I have this, I should just do this. And the basic idea is we're going to create a bank of noun representations. And these are going to be vectors for every noun. So for example, brush. We're going to make a bank of role representations. This is going to be a vector for every role. And what we're going to do is, when we want to predict a particular potential in this CRF, we're going to look up the noun, look up the role, and use a shared composition function across the whole system to predict what we expect to see in the image. And then we're going to take that prediction and test whether it's in the image. So we're going to do that for every single potential that we need to produce for this CRF. So that's kind of the general story. In practice, there's like a lot of details to like make it work. So we use kind of like this out tensor composition thing and some sort of like specific way in which we compute role representations. I just want to give you a feeling that, you know, there's this like particular machinery to make it work. Some ways of making it work don't work. So how well does it actually work? So we were interested in this yellow box. It turns out for this yellow box I'm plotting, on the red line is the original CRF performance. On the black line is this kind of new compositional CRF. And in the sparse range, on verb accuracy, it outperforms on every kind of point. Overall, this kind of approach leads to around 1.25 point increase on verb accuracy and a big boost on actually filling the slots in correctly, which is role accuracy. So it turns out that's kind of one approach. A kind of orthogonal approach towards dealing with the sparsity issue is actually looking at new ways of getting data into the system, right? Like the easy way to walk up that graph is just walk right, okay, instead of just trying to grab that curve and pull it up. And so the basic idea is, so when we predict these frames, or when we observe them at training time, one way to view them is actually as simple declarative sentences. Okay? So if you had a frame like this one, so this is a loading situation, you could kind of deterministically realize it as something like woman loading horse into trailer with rope outdoors. And it turns out some people at UIUC basically took some of the situation recognition models and trained a representation. If you just kind of add it to a caption generating system, the representation trained on situation recognition, you can just kind of get a boost on captioning, just a 1 point boost. And so the basic proposal is this. We're going to take this frame, and we're going to realize it as a sentence. And we're going to do this deterministically with a template. And then what we're going to do is we're going to take pieces of the sentence and just chop it up. So we're going to get something like woman loading horse, or woman loading with rope. Or we're going to exclude the woman and just say loading into trailer. And we're going to enter these phrases into Google and retrieve some images. And what we're going to do is we're going to pre-train our situation recognition model on these images to actually predict full situations, and then kind of fine-tune the model on the original data. And kind of like a central challenge is basically, well, you used to have this full frame, and now you've broken it up into like some sub-piece, and you've retrieved some images, right? So originally we thought there was a horse. We Googled loading into a trailer, and we got back a cow, okay? So the way we deal with that is basically, for the values which we haven't specified, we use marginal inference in the CRF. So we optimize the marginal likelihood that we say loading into trailer, and ideally that likelihood will assign high likelihood to this being a cow. So that's basically the story. It turns out kind of what we call this semantic augmentation. It turns out it helps the baseline CRF, and it actually helps our compositional CRF even more. And kind of the intuition behind this is basically lots of web images are very object-centric. So if you don't have good sharing between objects, it's hard to figure out exactly what's happening. Yeah. So I guess that's all I'm going to say about situation recognition. Just to kind of summarize, we presented a new formalism for events happening in images. We showed how you could use language resources such as WordNet and FrameNet to actually build up the problem. And then we showed how you can tackle sparsity by A, building better models, but B, actually using the connection to language to kind of get more data. Yeah.
When you're getting training data from Google, do you do any like human filtering, or do you just use it?
And just use it. Yeah. Yeah. So it's staged such that you first train on that and then train on the real data. Yeah. Yeah.
Do you think using statistics from just text, like eating pizza, is more common than eating elephants? If you look in text on.
Yeah. So I mean, that's my dream. I haven't really found a way towards getting like the right resources and the right set of extractions to get something like that. But yeah, that'd be really cool. Yeah.
Is your CVPR 17 submission available online?
Yep. Yeah. Okay. So the last thing I'm going to talk about is bias, and this is a paper I've been working on with Vicente, with his collaborators at Virginia, and it's called Men Also Like Shopping. And the basic idea is, okay, so we want to build this grounded intelligence. We don't want it to start over, right? So we hope that we're going to use some sort of resources or some sort of like linguistic context to speed things up, right? But where did this linguistic context come from, right? Of course it came from us, right? And so what extra things are we actually kind of putting into the model that we might not expect, that you know, will certainly make the agent learn faster, but might not actually be palatable for us in the long term. So kind of the first thing you want to do, I think, when you think about this problem is like, how do you identify, like, is there a problem, right? And so the basic idea is, well, what we're going to do is we're just going to count, okay? And we're going to count two things. So the first thing that we're going to count is, so we're going to pick some sort of demographic variable, for example, gender. So in this example, we're going to use male or female. And we're going to pick some sort of like output in our prediction system. So we're predicting situations here. And so we're going to try to count how often does the verb co-occur with your demographic variable. So here we're going to count, and we're going to see, okay, so cooking co-occurs with woman, once, cooking co-occurs with man once. So this is like 50-50, and we're going to look straight in the training data. So this in itself could reveal a problem, right? So you might find that there's like heavy skew, like females are more likely to be cooking under the training distribution, okay? But we're also going to count another thing. We're going to count how often does a model trained on this distribution on a new set of development images make the same type of prediction, okay? So what we're going to do is we're going to take development images, put it through a recognition system, take the top one output, and count how often does cooking, for example, co-occur with gender, male or female. So this is exactly this graph. I'm going to explain it. Okay. So along the bottom axis is the first thing we wanted to count. Okay. So this is how often does a verb, so every dot is a verb, co-occur with a particular gender indicating noun in the agent role. Okay? So in the ideal case, okay, every verb would be 50-50, right? So in the sense that there's no gender bias for verbs in a particular data set. It turns out for in situ, there's heavy bias, okay? So here are some examples. Cooking happens is female dominated, practically 2-to-1. Some verbs are extremely heavily dominated. So for example, combing is like 4-to-1. There are other male dominated verbs. So something like coaching tends to be male dominated, but also things like drinking, in particular like alcoholic beverages, tend to be male dominated. And so it turns out, at least in situ, 50% of verbs favor one gender or the other gender by a ratio of 2-to-1. So this in itself could be a problem. But it turns out something even worse has happened. Okay? So on the top axis, I'm evaluating a system trained on this data. Okay? What is its gender preference for a particular verb? Okay? And so in the absolute ideal case, that system on the development set would predict along this blue line, and we wouldn't have it's a biased data set, but we predicted at the bias. It turns out most of the predictions actually amplify the existing bias. So if you started with a cooking image that was favored 2-to-1, or a verb cooking which is favored female 2-to-1, you walk away with a predictor that's favored 3-to-1 for females towards cooking. Okay? I don't exactly know why, but there's some arguments you can make. So one thing that we know is that this trend increases with decreased confidence. So as the confidence of the predictor decreases, the bias amplification increases. So what that's saying is it likely doesn't know what's happening in the image, and when it doesn't know what's happening in the image, it bets on the bias.
It makes sense because you have the prior in the
Yeah.
posterior, and if you go with the posterior, you're only counting on the prior.
Yeah, it does make sense, but it's not ideal. And so
You can't expect your model to learn anything different from the data.
exactly, so ideally it would run along this blue line. Yeah, yeah,
So you're doing top one.
yeah.
What if you got the posterior distribution of the gender term?
Yeah,
Find that marginal distribution.
Yeah.
Wouldn't that give you a more accurate?
yeah, and I've done that version of the same thing. It looks very similar. Yeah.
It also shows that your model lacks grounding, right? So whenever it says
Sorry, what?
this behavior that you get more bias at prediction time versus what you are seeing in training data also shows that your model lacks grounding. So there are two semantic entities involved, cooking and woman. If the model was able to decompose cooking and woman,
Yeah,
it would be less biased at prediction time. But if it is learning that woman
Yeah.
implies cooking,
Yeah.
it would be heavily biased for
Yeah.
women for the verbs that are cooking.
yeah, absolutely. But so that's a two-edged sword, right? So in this context, that sounds really bad, but in the context of predicting the talking on the phone image, that was really, really good, right? Because there were no pixels for the phone. So it's, yeah. Yeah.
You've got red dots and black stars. What's the difference?
The black stars are just the named ones, yeah.
Have you tried coloring this based on how common the data is?
So it's no, I haven't. Yeah.
So the way you put it is kind of in terms of bad and good, but this strikes me as fantastic for the following reason. Not obviously for promoting gender biases, but for being able to start to quantify biases in your training data and biases due to amplification by the algorithm.
Yeah.
And so if you have a model that allows you to do that, that's extremely powerful to
Yeah.
apply to learning algorithms in
Yeah.
general. So
Yeah.
This seems really exciting.
Yeah. So, yeah, I'm also very excited about it.
Are you sure your depth distribution is the same bias? I'm thinking if you're trying to maximize accuracy, why would it amplify, or why would the system
So the dev set is large. It's 25,000 images. And I think the answer to the second one is basically I think it's likely amplifying it because it doesn't know what's in the image. And so it's making a bet. It's just a bet that probably we're uncomfortable with. OK. So yeah, so I guess I had the summary statistic. Basically, the average magnitude of amplification across all the verbs is about 5%. And it turns out the higher the initial bias, the more amplification you can expect. We've actually developed, so I've identified two problems, and I don't really know what to do about the first one, that the initial data set is biased. But we have been developing some algorithms to deal with bias amplification. Okay? And the basic idea is we're going to introduce some corpus constraints at prediction time to actually help us kind of mitigate the amount of amplification we're going to do. And so let's imagine we're a system. It's trained. It's made this prediction. So it's made one prediction that's an agent, which is cooking, which is female, another prediction, which is agent, which is cooking, that is female. We know from the training distribution it was some number. It's not 1/2, but in this example, it's 1/2. What we're going to do is we're going to count the number of kind of predictions that we're making in the development set. So we're going to say it's 2. And what we're going to say is there's a violation if this ratio differs from the original training ratio. And if there's a violation, what we're going to do is we're going to try to make a global adjustment to the potential in our CRF to reduce this bias, or this bias amplification. So basically, I'm not going to go too in the technical details, basically out of time, but we formulated an ILP for this. And because we're kind of using structured prediction, we can actually solve it using dual decomposition and kind of reusing the original kind of inference routines for the structured predictor. So how well does this actually work? So this is the same graph I showed you before, only it's color-coded. Okay? So we're going to say that there's a violation if it exceeds the original distribution by some margin. So the margin is this dotted blue line. The original distribution is the solid blue line. I color the points which are within the margin as green, and I color the points which are outside the margin as red. These are violations. So once we actually apply our method, this is what it looks like. So in general, the whole thing has been kind of squashed in, and there's many more green points. It's a little hard to see. But it turns out we can actually reduce the amount of bias amplification by around 45%, and there's actually basically no loss in actual underlying system performance. Yeah.
So if you took this to the extreme and you were just like grab a coin.
Yeah.
When I look at all coins, it's like heads is like 2/3 probable. And then I'm asked to make 50 predictions over the outcome of that coin flip. Why would I want to make 2/3 of those heads in the absence of, as opposed to all of them heads, in the absence of further information? Why this focus on making sure that it is the same, like 2/3?
Yeah. So the issue isn't the accuracy of your prediction. The issue is kind of like what's the cost of being mistaken, and how does that, like, do we feel comfortable with presenting that kind of amplified distribution to a potential user?
So, but this means that the bias is only problematic in particular classes.
Yeah.
Okay.
Yeah. So, I mean, you don't want to mess up the bias you set up for the phone, because you probably don't have a problem with, phones being over-predicted for this particular pose. But
But it does become a bit of a problem. You're addressing it this way there, but in the absence of this further information, you make these predictions one by one, not globally.
Yeah.
So I don't make 50
Yeah.
coin flip predictions
Yeah.
at the same time.
Yeah.
So what would be the answer there? Would
Yeah.
I have to take them in batches?
Yeah.
And what would I do?
yeah. So, I mean, I think this setup only really matters if you're doing you're doing predictions at large scale, right? In which case the batch setup actually makes sense. So if you're Google making kind of predictions for like users about what's in images, they should be able to balance in batch. if you're an individual kind of doing this, like it's not even really the right setup because it's like some sort of personal use, right? It doesn't necessarily like affect us as a whole, as a community, but yeah. Yeah.
So these results are on test sets, so you have a training set, a dev set, and a test set,
Yeah.
is that right?
Yeah.
And on the left hand, are you training on just the training, or are you training on the dev?
Okay, so the setup is you train a predictor on the training set. Okay, you're going to do dev predictions. I don't use any of the dev labels, but I'm going to use the training distribution, and I'm going to predict the dev set in batch. And when I do that prediction in batch, I'm going to run an optimization to make sure that the variables are more
It
under.
seems like, if I understood what you're doing, in the right side curve there, you're changing the prediction as a result of the dev set with this ILP. And I'm just wondering if you want to compare against training on both the training set and the dev set. On the left hand side, you're not actually using the dev set at all.
We're not using any of the dev labels. We're using the system predictions on the dev set, and we're using the training distribution. So it's make your predictions unbiased, not make them more in line with the dev distribution. So there is a version of this that basically like you find some sort of global bias weights to like reweight your like test set predictions so that you can like do it streaming, but we haven't like worked that out and to actually like see if we can build those models. But that's another like way you could tackle this. You could like say, I'm trying to find a set of global weights that I can apply per image and just apply them one by one as I get a dev image. But yeah. Okay. So that's basically it. So just to kind of summarize, I've talked about how you can use kind of like language resources in multiple different ways to kind of build up intelligent systems, intelligent grounded systems, ones which like start in the world and then get better by using language resources, ones which need language resources to like kind of start up, but then you kind of get new problems and really can like quantify, for example, what's happening in an image. And then I talked a little bit about, well, if we're going to do this, like, what are we actually implicitly kind of like sneaking into this? And is there a way to kind of address some of those problems? And so I wanted to spend maybe like 5 seconds talking a little bit about like what are my ideas going forward. And so kind of like in this theme of grounded intelligence, I guess there have been a lot of questions, like Peter said, like why haven't you used like real language, right? Really, at the end of the day, what we've used is like ontologies, right? And they were like big and they're like based on language, but there are no sentences. And we're running out of ontologies. So there's WordNet, there's verb resources, which like are super few in between, but then that's like kind of it. Like how do we move forward? And kind of like to think of this in context, as like, let's say we want to build like new recognition problems. Okay, so let's say we wanted to define something like a graph over an image, right? So here the graph is like relating like all the entities that we would like normally consider objects and kind of like labeling relations between them. Like if this was our data, right, the thing that would happen is we'd like, first of all, we couldn't make very much of this data, right? Even though it might be like something we really want to predict. Right? So we expect to see a few examples. And for the examples we see, there's actually like higher order structures, which we'll observe ever more rarely in the world. Right? So I think in this kind of context, reading will actually kind of become more important. Because the question is, where do you actually get the signal to like train up the parameters to do this kind of problem? And that kind of intuition actually already happens. So in like things like VQA challenge, they're this like giant heavy tail of things like that you see only just a few times. So like, why is the man upside down? How do you answer that question? Are you ever going to see enough images to actually just statistically be able to say upside down people are falling off of horses? Or are we actually going to need to bring in other resources? So that's kind of what I'm thinking about. And I guess that's it.